For over half a century, hardware engineering relied on a single mathematical model to predict performance, Amdahl's law. It was built on the premise that you scale a computer by simply stamping out an infinite grid of identical logic cores. Under this classical model, potential speedup is calculated using just two variables: the total number of processors, n, and the fixed fraction of the workload that can be run in parallel, p. That equation relies entirely on three assumptions. Compute units are strictly homogeneous, scaling happens purely through replication, and software divides cleanly into fixed serial and parallel chunks. Modern system-on-chip architectures do not behave this way. You cannot scale a modern smartphone or data center chip by blindly pasting identical CPU cores across the wafer. The old variables are physically disconnected from the silicon we actually built today. To understand where hardware is actually going, we have to abandon the 1967 mathematical framework. Speedup via replication is a dead concept. The true constraint on modern processors is not the number of cores, but physical die area. This abstract floor plan illustrates the modern engineering reality. A strict bounded area must be divided between general-purpose programmable logic and specialized fixed-function accelerators like tensor engines or media decoders. Therefore, we replace processor count with a new mathematical foundation, the hardware allocation variable, x. The variable x represents the specific fraction of your total hardware budget allocated exclusively to specialized logic. It slides between 0 and 1. This is a zero-sum trade-off. Every square millimeter of silicon you dedicate to a fixed-function accelerator is a millimeter stolen from the generalized programmable compute fabric. The central architectural question is no longer about buying speedup with more cores. The question is how to perfectly allocate constrained area between fixed and flexible hardware, especially when the workload itself keeps changing. To balance that silicon budget, we first have to discard the classical parallel fraction of software. It is too narrow a definition for modern computation. Instead, we introduce a new structural metric, S, the value scalable fraction. S represents the portion of a workload where feeding the system more compute continues to generate measurable qualitative value. It does not just execute a fixed task faster, it delivers a mathematically superior result. Contrast this with traditional bounded parallel tasks. Standard rasterization in graphics is highly parallel, but it is bounded. Once the pixels are shaded, throwing twice as many processors at the task just increases frame throughput. The image itself does not get any better. We see this physical proof in modern neural rendering. In this low-sample Monte Carlo render, the raw, noisy geometry acts as a bounded acquisition step. In modern pipelines, that raw acquisition data is immediately handed off to a neural denoising and reconstruction stage. This output image shows the result of that neural pass. The programmable algorithm extracts high-fidelity details and exact lighting from the noisy baseline data. That neural reconstruction stage belongs entirely to the value scalable fraction, S. If you allocate more compute to it, through a larger model or longer inference time, the delivered visual fidelity continuously improves. This migration defines the modern workload structure. The most expensive, value-producing work moves away from fixed acquisition steps and heavily concentrates in dynamically scaling late-stage computation. By splitting the software into a bounded portion and a value-scalable fraction S, we can write a modernized execution time equation. We introduce one more variable, the efficiency ratio, R. This measures the exact performance advantage that a dedicated, custom accelerator has over a general programmable core. But there is a strict limitation. That massive efficiency boost only accelerates the bounded portion of the workload. It does nothing for the scalable neural tasks. This models execution time. The left term is bounded workload divided by specialized efficiency. The right is the scalable fraction on remaining programmable area. Graphed for a 20% scalable workload, time forms a U-curve. The lowest dip represents optimal hardware allocation, X star. Because X star is well above 0, the math proves stealing die space to build a custom accelerator clearly reduces your total execution time. If workloads remained static, domain-specific hardware would always win. But as S grows, the optimal allocation point moves. To find the breaking point of this allocation model, we take the first derivative of the execution time equation and evaluate it at the origin. Setting that derivative to less than 0 creates a strict mathematical inequality. It dictates exactly when specialized silicon is actually viable. By isolating the value-scalable fraction, we reveal the collapse threshold. SC equals exactly 1 minus 1 over the efficiency ratio, R. This plot translates the resulting calculus into a physical race diagram for silicon architects. We chart the value-scalable workload on the horizontal axis against the accelerator's efficiency advantage on the vertical axis. This curve represents the absolute minimum efficiency an accelerator must achieve just to justify existing on the die. If the workload crosses into this upper territory, the math breaks down. The optimal area allocation for specialized hardware falls exactly to 0. The threshold is a finite wall, not an asymptote. As the scalable portion of a task grows, the efficiency bar required for a custom chip spikes so violently that specialization becomes mathematically unjustifiable. This exact mathematical collapse explains the real-world evolution of the graphics processor. This block diagram maps early 3D rendering. It relied heavily on fixed-function pipelines because the value-scalable fraction was tiny. The visual data was mostly finalized during the initial visibility passes. The introduction of AI-driven frame generation, denoising, and upscaling structurally altered the workload. The initial visibility passes shrank into basic acquisition steps, while the programmable tensor stages expanded to absorb the vast majority of the compute budget. As the most expensive work migrated to late-stage neural inference, the S variable spiked, driving the entire rendering pipeline straight into the collapse region. This is exactly why GPUs abandoned fixed-function shading hardware and replaced it with unified, entirely programmable compute fabrics. We see the exact same allocation logic governing modern AI hardware. Narrow, domain-specific AI accelerators perform well early in a product cycle, while computational boundaries are rigidly fixed. Fixed-function ASICs struggle as software optimization, sparsity, and new model architectures relocate where the value is produced. Programmable hardware, like modern GPUs and generalized TPUs, serves as a flexible substrate, absorbing the migrating scalable workload. Specialization is not a permanent victory. It must continuously re-earn its area. In the race against scaling laws, generalized compute prevails because it flexibly adapts to wherever additional computation creates the most measurable value.